Yeah. Hello. Good evening. Hello.
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 Yeah. Okay. So today we have the session for week 8. So we can start now. So all of you have gone through the content.
Yes, ma'am.
Your voice is not audible.
It is not audible. Hello.
Your voice is audible.
Audible, right? Okay. Okay. So we can start now. Yeah. So any doubt from week 8?
8.4, question number 4.
Sorry, 8.4.
Question 4.
Wait. 8.4. Okay. So you have n random variables that are IIT normal mu sigma square. I will just write the question first and then I will share my screen. The square is 1 upon n sum over xi square 1 to 1 minus x bar square. And we have to find the bias of theta hat square. Okay, it's visible, right?
Yes, ma'am.
Okay. Okay. So we have this is AQ 8.4, question number 4. Now it is given that you have n IID samples. So you have x1, x2 up to xn n IID samples, and they are coming from normal mu sigma square distribution. And we have to find the estimators. We have to find the bias of an estimator. So we have an estimator given for our unknown parameter sigma square here. So we have, let's say the estimator for the sigma square is given by sigma square hat, and this is given to us as 1 upon n sum over xi square. I is varying from 1 to n, this minus x bar square. So what is the formula for, like, how do you find the bias? Can you tell me how do you find the bias? So if we have, let's say, a parameter theta, a known parameter theta, and the estimator for theta is given as, let's say, theta star, then how do you find the bias of theta star?
Expectation of theta star minus theta.
Right? So the same thing we'll do here. So if I have to find bias of theta hat square, I will have to find expectation of theta hat square minus expectation of theta
Mu square.
expectation of sigma hat square minus expectation of sigma square. So that is just sigma square. Now, how do you find the expectation of sigma square? This is the tricky part here. So you have to find expectation of theta hat square. Sorry, sigma hat square, and this is equal to expectation of 1 upon n. So theta hat square, I'll just take it from there. Sum over xi square, I varying from 1 to n, minus x bar of square. So using the property of expectation, I can separate it and write it as this term minus expectation of x bar square, right? So what is the formula for variance? What is the formula for variance? If I have to, let's say, I have a random variable x and I have to find the variance of x, what will I write?
Ex square minus
Expectation of the random variable x square minus
ex ka whole square.
expectation of x ka whole square.
Whole square.
Okay. So now we have here expectation of, so what is x bar? What is x bar? What is x bar?
The sample mean.
Yeah, but it is a random variable, right?
Yeah.
So we know that so this x bar is just a random variable. So let's say I will write it as expectation of y square. So if I have to write in this form, what will I write? I will write expectation of y square as variance of y minus plus expectation of y whole square.
Whole square.
So in this case, our y is x bar. So this is nothing but variance of x bar plus variance of x bar. Sorry, this is expectation, right? Expectation of x bar whole square. So if we have n samples, if we have n IID samples, so what is the expectation of x bar? And let's say if this x has the distribution with mean mu and variance sigma square, then what is the expectation of x bar?
Mu.
Mu. Sorry. Can you see the screen?
Yes.
Okay. So expectation of x bar is mu, and what is variance of x bar?
Sigma square by n.
Sigma square by n.
Yeah.
Now what is, so I will just write here as this is sigma square by n plus mu square. So this is nothing but expectation of x bar square. This is this term. Now still we have to find expectation of 1 by n sum over xi square. So this I will do it here. So now we have to find expectation of 1 upon n sum over xi square, I varying from 1 to n. So 1 by n we can pull outside. So if we'll pull it outside, we'll have 1 by n expectation of sum over xi square. Again, the same thing that we have done here, as variance of x can be written as expectation of x square minus expectation of x whole square. The same thing we can do over here. So if you can take the expectation inside, that is a property. So you can take the expectation inside and you can write sum over expectation of xi whole square, I varying from 1 to n. So if you do the same thing here, you will get 1 upon n. This is going to be variance of xi square plus expectation of xi whole square, right? So what is the variance of xi square? And there is a summation over here varying from 1 to n. So what is the variance of each of the xi?
Sigma square.
Sigma square. And what is the expectation of each of the xi?
Mu.
Square. So this is mu square. So you have to sum it over. So you have 1 by n, sum it over, I varying from 1 to n, sigma square plus mu square. Correct? So this, if you sum, you will get n times. So this n and n will get cancelled out. So you will just have sigma square plus mu square. And from this part, minus expectation of x bar whole square, you have minus sigma square by n plus, sorry, so this will be again here minus. So this is over minus square. So this is what? This is just expectation of, this is a expectation of sigma hat square, right? So you will have sigma square minus sigma square by n. And to find the bias, so according to the bias definition, you will have to, that is what, that is expectation of sigma hat square minus sigma square. So you will have to subtract sigma square here. So if you subtract sigma square here, then you will just get minus sigma square by n. So this is your answer. Is it okay?
Yes, ma'am.
Okay. No doubt over here, right?
8.6 question number 2.
8.6 question number 2. Okay. AQ 8.6 question number 2. Okay. So here you have a uniform distribution lying where x is uniform in 1, 2, 3 up to n, and you have to consider a sampling from the distribution x, and you have to find the maximum likelihood estimate of n. Okay. So how do you find the maximum likelihood?
By multiplying PMF.
Yeah, continue.
And the maximum value of then differentiated and equate with 0. Then we find the value of unknown quantity.
Yeah, right. So can you try? Can you try this problem? Can you try it now? Can you try this problem right now? Just try to yeah, whatever you just said, just try to implement it, and then let me know where you're getting the doubt here.
Hello, ma'am. 8.3 second question.
8.3 second question. Okay. Yeah. So again, can you tell me where is the problem in this question? Like, what is the part that you're not able to get it? Mm, I
As
will. Yeah.
equality.
Huh?
See, I can directly substitute n, right?
You can directly substitute n, but where is the n? N is not given to you. Do you know the value of n?
1 minute. Because when I tried,
I will just write the problem here.
Ma'am, likelihood comes 1 by n to the power 13.
1 by,
N to the power 13.
okay. Just let me see. Wait. Okay, so that is AQ 8.3, question number 2. You have to find probability of error. Greater than equal to 100 mu by 10, right? 0.01. Is this a problem? And you have nu hat to be x1 up to xn by n.
right.
And all these samples are coming from Poisson mu.
IID person. Yeah.
Yeah. Okay. Yeah. So what is error again?
Error is theta hat minus theta.
Okay. So you know error is theta hat minus theta. So in this case, what is your theta?
In this case, theta is mu.
Theta is mu. And what is theta?
Theta hat, you mean?
No, in this case, theta hat is mu hat.
Yeah,
And what is theta?
mu.
Mu. So all these samples, this here x1, all these xi are coming from
Poisson
Poisson lambda,
lambda. Yeah.
right?
Mu
Uh,
basically. Yeah.
yeah. So you have to use Chebyshev's inequality to find the value of n, right?
Right.
So what will you do here? This is probability. Okay. So our mu hat is nothing but x bar. Correct?
Mu hat is x bar. Okay. Yes.
And what is mu?
Mu is mule.
Mu is lambda here. Mu is lambda here, right?
Okay.
Mu is lambda, right? What is mu? Mu is mean.
Mean of it. Yeah.
Mean of the distribution. That is lambda.
Yeah.
So, okay. Can you tell me what is Chebyshev's inequality?
Variance square by.
No, tell me the complete Chebyshev's inequality.
So basically probability of error minus.
No. Tell me the Chebyshev's inequality, not with error. I mean,
Okay,
if
x.
you have,
Probability of x minus x bar.
okay.
is greater than
Probability of
Hmm.
mod of x minus mu.
Yeah, right.
X minus mu greater than equal to c
Hmm.
is less than equal to
Hmm.
variance of x by c.
A variance of x by
C
it is c square.
is
So this is a Chebyshev inequality. Now, can you relate it to this problem? What is your random variable here? So this is your Chebyshev's inequality. Now, if you have error as in you have now mu hat minus mu. Okay. So what is the random variable here?
mu
mu
hat.
hat.
Mu hat is a random variable, right? And what is mu?
Lambda.
No, mu is the mean
Constant.
of no mu is the expectation of mu hat, right?
Yes.
What was mu here? Mu here was expectation of the random variable x. So here also mu is your expected value of the random variable mu hat, correct?
Yeah, that's right.
Now this is your error, and this is greater than equal to under root of mu upon 10. So this is your basically delta. So I will write this is as delta. Okay. So according to Chebyshev's inequality, what should be the what should I write here?
Variance of
Mu hat.
So this is going to be less than equal to what?
Variance of mu hat
Variance of mu hat, yes,
divided by mu by 10 square.
mu by 100. Now what is variance of mu hat?
one by n square into
1 by n square. Why is it 1 by n square?
property of variance.
Sorry. What is mu hat?
x1 plus, 2xn divided by n.
This is a mu hat.
Right.
So what is the property of variance? See it here. So mu hat is x1 plus up to xn by n. Now how will you, let's say all these xi's are IID x, where mean is mu and variance is, let's say, sigma square. So if I have to find the variance of mu hat, so how will you find it?
x1 by n whole square.
1 by n square into n into variance of x.
Yeah, right. So it is going to be, so since this 1 by n is a constant, this constant term will come outside and it will be 1 upon n square. Now inside we have just variance of x1 up to xn. Now since all these xi's are IID x, so this you can write this as 1 upon n square times variance of x1 plus up to variance of xn, right? Since these are independent, so we can split it and write it in this way. Now each of these xi's are IIDx, so we can add all this, like all are identical. So this is just n times variance of x upon n square. So this is going to be variance of x upon n, right?
Yeah.
So always remember that whenever you have, so you can directly say it from here, that this is your sample mean. This mu hat is nothing but your sample mean x bar. So whenever you have the sample mean, your expectation of sample mean comes out to be mu, and variance of your sample mean comes out to be sigma square by n. Like this thing you always keep in mind, like it is very useful. So again, if I go back here, so I found it is sigma square by n, right? Variance of x by n. So what is variance of mu hat? Sorry, variance of x. So what is variance of x? So what I found is it is nothing but variance of x by n, correct? So this is nothing but variance of x by n, and this is, let's say I will write mu 100 here and mu here. So what is variance of x?
Lambda.
Variance of x is lambda. So I will write this is lambda upon n. So mu is also lambda into 100 less than equal to 0.01. So n is going to be greater than equal to 100 upon 0.01. Right?
Yeah, I think I mean I had a problem with the variance, the calculation of variance.
So this thing, this part you always like keep in mind, and like try to derive it first on your own, like
Yeah.
how the expectation of x bar is mu and how the variance of x bar is sigma square by n. Then you will remember this automatically.
Yeah, sure. Thanks.
Okay, coming to AQ 8.6. Who had asked the question? Yeah, Abhijit. So AQ 8.6, problem number 4. What was the number? 2. Okay. Yeah, you said it is coming out to be 1 upon n to the power 13. Correct?
Yes, ma'am.
So what was given as okay, what was given as that x is uniform in 1 to n, where n is unknown, and you have a sampling from the distribution x and find the maximum likelihood estimate of n. So you had the samples from a uniform distribution, which is from 1, 2, 3 up to n, where n is unknown. And you have to find the maximum, like you have given some 13 samples, correct?
Yes, ma'am.
You have given some 13 samples. Now, okay. So what is likelihood function? So if I write LXI of theta, so this is nothing but product of fx of xi of theta, right? Where I is varying from 1 to 13 here. Now you have, if you do the product, you will get 1 upon n, same as it is 1 upon n to the power 13. Now you want to maximize it, correct? You want to maximize this likelihood function. So if you look at your samples, so the samples are 1, 5, 4, 8, 11, 9, 15, 17, 6, 3, 13, 27. So when will you get the maximum value?
when n is less.
Hello.
Ma'am,
Yeah. So I'll just write down the samples here. Wait. Okay. So your sample is
154,
yeah. So it is 1, 5, 4, 8,
8,
11, 9, 15, 17, 6, 3, 13, 20, 7. Something great.
Excuse me, ma'am.
Yeah.
And we can use a condition that n will be at least greater than or equal to all the samplings that we are given, like 1, 5, 4. It will be greater than at least all of them. So it should be greater than even the maximum of these samplings, which will be 20.
Yeah. Right. Yeah. Who's there?
Sakshi.
Yeah. Sakshi. Yeah, that was right. So yeah, the same thing. If we that the same thing we have to follow here, and then directly we can say that since each of the samples lies between like maximum value that it can take is 20, right? So this is a maximum likelihood estimate.
Ma'am, 8.7, question number 3.
0.7.
Question number 3.
Okay. Okay, again, the same logic you'll have to use here. So in this case, you have X to be uniform between A and B. And what is the distribution function? What is the distribution function of when X is continuous between A to B? It is 1 upon B minus A, right?
Yes, ma'am.
Yeah. So if X is uniform between A to B, then its distribution function is given by 1 upon B minus A. So again, you have how many sampling? You have n samples here, correct? Now, if you do this, if you find the likelihood function, so what will you get?
1 by B minus C ka power है.
1 minus b to the power 1 upon b minus a to the power n, correct? Now you have to find the maximum likelihood estimator
Ma'am,
of.
your screen is not visible.
Oh, okay. It is visible now.
Yes, ma'am.
So in this problem, you have given x is uniform in A to B, right? Now, what is the distribution? 1 upon B minus A. So the same thing what you have done there. So in this case, you have to find the ML estimator for A, right? So the same thing you apply here. So you find the likelihood function, then using the same logic that we have used in the previous problem, this will work here. Did you get this part?
No, ma'am, solve this.
No. See, if you find the likelihood function, so you will get what? It is 1 upon b minus a to the power n, right? You have to find the ML estimator of the parameter a. Now you see that this X is uniform in A to B, right? So you have A and you have B here. And we are saying all the samples are coming from X. So all of these will be uniform in A to B. So all of your sample, let's say X1, X2, X3 to Xn, all these are lying in A to B. Fine.
Yes, ma'am.
Now you have to maximize this. You have to maximize your L. So when is it possible? So whenever like if you take A to be minimum of all these samples, when you take the minimum of all the samples, it is going to be your it is going to maximize your likelihood function.
Yes, ma'am. I got one.
You got it?
Yes, ma'am.
Okay. Okay, anything else?
Ma'am, I have a doubt in lecture
Yeah.
8.8 lecture.
Lecture 8.8. What is the doubt?
Around 12 minutes 10 seconds.
12 minute. Wait.
That you saw.
12 minutes.
So one good principle. Remember, it's easy proof.
Yeah. Do you have problem in the proof? Like how did you
Yes,
find
ma'am.
the I will share a Discord thread. You can check the proof there.
Okay.
I will share it in chat box. Wait, 8.8, right?
Here, ma'am, here professor directly found W1 by N.
Yeah,
did
yeah.
not-
I will send you the proof. Just give me a second. Yeah, somebody had posted already. You can check the proof there. So I'll just tell you what we are doing here, doing there. So I'm not sure if you are aware of partial differentiation.
Aware, ma'am.
So the same thing you will have to do here. Just you'll have to consider one as a constant and then differentiate using the other one. Just check the post. Maybe it will be clear to you.
Okay, ma'am.
Okay. Yeah. Okay, anything else? Any other doubt? So how is week 7, week 8 going on? Is it difficult? Is it easy?
Easy, ma'am.
Easy. Okay. Yeah, nobody has any doubt? You all tried practice assignment, tutorials.
Hello, ma'am. Excuse me.
Yeah.
Solution to the quiz one hasn't been uploaded in the portal.
Yeah, the solution for quiz one will not be uploaded. So the solution for quizzes will not be provided to you. So
Only the answer keys are available. That's why I'm asking.
yeah, only the answer keys will be available. Yeah.
Thank you.
So
But someone has solved and posted in the discourse forum, I think.
yeah, I had actually referred to that one.
Yeah,
Maybe Sakshi, I think. Or
I forgot the name. Yeah, they have, someone has posted the solution. They have solved it and posted the solution.
yeah, right. So how was the quiz one for everyone? You're satisfied?
Time was a problem for me.
Yeah.
And yeah, it's a little bit difficult. Yeah.
Yeah, prepare well for the second quiz.
How did the score look at your end? I mean, you have better visibility to the scores, Nikita. So can you give some idea how everyone fared out?
Okay, so the result was, I won't say very bad, but yeah, according to the paper, I will say it was decent.
Okay.
Yeah. So
So we
maybe,
had very good
yeah.
statistics figures. I mean, when the qualifier was conducted, then there was a very good session where the statistics around the marks and everything was given across to us. But after
Okay.
that, we did not get a chance to see any of the scores of how the
So
overall thing is developing.
those, yeah, so those details were given only for the qualifier.
Yeah, yeah.
It will not be provided for the later courses.
Hmm.
So I hope you all do very well in quiz two.
Hello, ma'am.
Yeah.
Yeah, I have one question that these activity questions solutions are provided anywhere. Is there any link or anything?
No, we don't provide the solution from our side, but I'm sure many students are posting the solutions on this course. And somebody has also created a drive link or something, and they're putting the solutions there. So you can check the discourse also sometimes. Like most of the problems are solved for the activity at least. So almost all the problems are solved there.
Okay, thank you, ma'am.
Yeah. Okay, so if you don't have any doubts, so what do you want to do now? Have you all solved the tutorial problems?
No, not yet.
Not yet. So maybe we can try few tutorial problems then.
Nikita, just one question. We had this formula sheet given in the exams
Huh.
with more weeks gradually passing.
Hmm.
Will the formula sheet have more formulas, or what we have just seen till week 1 to 4 only, those will be the formulas that will be provided? Because now gamma distribution also has come, and the
So
formulas of everything.
uh, in that formula 5, you already have the gamma distribution, beta distribution. Did you check that?
I I did
It is
check,
it
but
is it is there. Like for the discrete distribution, then on the second page for the continuous distribution, you have the distribution name, then it's PDF, CDF, expectation, variance, everything is
so the
given there.
formulas, when what I mean is asking specifically, for example, from week 8, we have seen the formulas of um, um, M1, M2, theta minus
No. You will
square,
not see
not at
all
that
those.
level.
No,
Okay,
not at that level. So only the
distributions,
distributions and
their
you also have
expectation
seen
and variance.
Markov, Chebyshev. So as
Yeah.
week,
Okay.
yeah, maybe week 7 you will have CLT, week law of large number.
Okay.
So important theorems, I can say.
Fine. Thank you.
Okay, so okay, let's try some problems from tutorials. Okay, so first you can try tutorial 1, question number 1. So I will write the problem for you here. So tutorial 1, question number 1. So it says you have some n samples, x1 to xn. Expectation of each of the xi is given to be mu, and variance of each of the xi's are given to be sigma square. Now you have two estimators. One is mu1 hat, that is given as xn, and other is mu2 hat, that is given as sum over xi, I varying from 1 to n, 1 upon n plus 1. So you have to check. So the problem is check for the biasness of mu1 hat and mu2 hat. So you just have to tell me whether uh, which estimator here is biased and which one is unbiased. So are you all trying the problem?
One is biased.
Sorry,
One is biased.
mu1 is biased. Okay. What about mu2?
Unbiased.
Okay.
Mu1 is unbiased and mu2 is biased.
Okay. So we have two answers here. So which one is correct? So, okay, somebody else has also answered unbiased and biased. Okay, so how will you check the biasness again?
If its bias is 0, then it is unbiased.
Yeah,
And-
right. Otherwise, it is biased. So again, to check the bias, we just have to check for the expectation of mu1, expectation of mu hat minus mu. So once you do this, if it comes out to be 0, it is unbiased. Otherwise, it is biased, right? So in this case, this is the right answer. Mu1 hat is unbiased and mu2 hat is biased. So whoever told mu1 hat to be biased and mu2 hat to be unbiased, please check your calculation once. Okay, can you try problem number 10 and 11? Question 10, question 11 from tutorial 1. So are you all trying the problem? Are you trying the problem?
Yes, yes, ma'am.
Okay, yeah.
One line is confusing. Estimator of 1 by lambda. Usually it will be given as a function, right? That word is confusing.
Wait. So you
Yeah.
have two estimators here. Lambda 1 hat
Yeah, it's given as
is x bar and lambda 2 hat is n times minimum of
yes.
x1 to xn.
Yeah.
So your estimator here is 1 upon lambda. I mean, sorry, estimator of 1 upon lambda. You have to, it is given. So you have a parameter 1 upon lambda, and the estimators for that parameter is given as x bar and n times minimum of x1 to xn. So use the usual process.
I
Like
think
whatever.
is it expected value is twisted and given, right? That's what I understand.
Sorry, expected value.
Is given in that word sentence. It is twisted and given as.
So for exponential distribution, your expected value is 1 upon lambda.
That's what it is expressed as that word, right?
Yeah. So use the usual process, then try to solve it. Is the first problem done? Question number 10.
Yes, I'm getting unbiased.
Okay.
Second one, I don't know how to approach it.
All right. What is lambda 2? N times
Minimum
Minimum
of
of x1 to x1.
minimum of samples. Okay. So for the first one, you are getting unbiased. Okay, so that is right. Problem number 11, you're not able to solve, right?
I don't know how to the function works because it's minimum of x1. How can we?
Yeah. Okay, so let's see. So this is a lambda 2 hat that is given as n times minimum of x1 to xn. So if we have to find the biasness, if we have to check, basically we have to find the expected value of lambda 2 hat, right? So first we'll have to know what is the distribution of n times basically minimum of x1 to xn, correct? Once we know the distribution, that is easy to identify. Now, how will you find the distribution? So go back to your week, first 2 weeks or second week where you have studied the maximum and minimum of random variable. So if let's say this is your z, if I have to find the distribution of z, what will I do? I will do probability z less than some z, right?
Yeah.
So in this case, your z is minimum of x1 to xn, and let's say this is less than equal to some small z. Now again, what will you write?
Less than
1 minus probability that minimum is greater than equal to z, right? This step is fine. Is this step fine?
yeah, but then why are we writing? Because usually greater than or z, we will go for 1 minus less than or equal to 2.
Oh, sorry, less than equal to it. That is by mistake. Less than equal to. Sorry. No, it was less greater than equal to. No. Yeah, what is the doubt? Tell me again.
No, why are we going for 1 minus?
Yeah, so can you
Generally
recall
for
back?
greater than z,
Can you recall back from week 2? Like if we have some random variable x1 to xn and their minimum is less than equal to z. So can I say if the minimum is less than equal to z, all of them are less than equal to z?
yeah.
No, right?
no, ma'am.
No, okay.
No,
Yeah.
because
So, no, yeah.
is it clear why it is no?
Yes, yes. Yeah.
So this is nothing, this minimum of x1 to xn is nothing but a random variable, which is z. So this is a sum event. So this we can write it as 1 minus probability z greater than equal to z. It will be same.
Okay.
So probability that some random variable is less than equal to z is same as 1 minus a complement, we write, correct? So a complement is z greater than equal to z. This is fine.
Yes, yes.
Now once I write minimum is greater than equal to z, it means each of the random variable is greater than equal to z. So this I can write as probability that x1 is greater than equal to z up to xn is greater than equal to z. And since each of these xi's are IID, I can just multiply it, right? and their ID x, they all are exponential lambda. So I will write 1 minus probability x is greater than equal to some z to the power n. Is this okay?
Yes.
Huh? Now again, this you can write it as 1 minus probability x is less than equal to z. Correct?
Yes. Yes.
Huh? Now this is same as 1 minus fx of z to the power n. And what is fx of z? X is your, let's say this is your x, and this follows exponential lambda. So their CDF is given as 1 minus e to the power minus lambda x. Correct? So in this case, we will write 1 minus in 1 minus e to the power minus lambda z to the power whole power n. So this is going to be 1 minus e to the power minus lambda, n lambda z. Correct? So can you see these two are of the same form?
Yeah.
Huh? So even this follows your exponential distribution. So even this is your exponential distribution with the parameter n lambda. Fine.
Yeah.
So now go back to the our original question. So this minimum of x1 to xn, this follows exponential n lambda. So if you find the expectation, so the expectation of n times, let's say I'm writing this as z. So this is going to be n times expected value of this z. And what is going to be the expectation of n lambda?
1 by n lambda.
1 upon n lambda. So n upon n lambda. So it is again going to be 1 upon lambda. So again, since expectation of 1 upon lambda 2 hat is coming out to 1 upon lambda, and our original estimate, original parameter was again 1 upon lambda. So again, it is going to be unbiased.
Yeah.
Right? Okay. Okay, so next we can try the problem from tutorial 2. Tutorial 2, question number 2 and 3. Tutorial 2, question number 2 and 3. I will write here the question. So X is given to be a discrete random variable and its PMF is given in this table. So you have X, you have fx of X 1, theta by 2, 2 theta by 3, and 3, 6 minus 5 theta upon 6. So this is a random variable X and the PMF is given by this. Now you have taken a sample and there 1 occur 10 times, 2 occur 20 times, and 3 occur again 20 times. So in question number 2, you have to find estimation, like you have to estimate theta using method of moment. And in problem 3, you have to estimate using maximum likelihood estimate. So let's try to do this problem. We'll just give you 2 minutes, 2 to 3 minutes, then we can discuss. Okay. So what is the answer for this question number second part? Are you all trying the problems? Okay, so how will you find the method of like how will you estimate the parameter theta using method of moment?
I haven't completed the second half, ma'am. So
Okay, try.
We got expected value of x with x bar.
Yes, right.
And expected value of the random variable I got as 3 minus 4 theta by 3.
3 minus 4 theta by
3.
3.
No,
Okay.
only denominator 3 is only for 4 theta.
Uh,
So 9 minus 4 theta by 3.
9 minus 4 theta by 3.
And
This is your expectation, right?
yeah, x bar I found as 11 by 5.
X bar 11 by 5.
Yeah, so from here we'll get theta as 6 by 10.
Okay. What about the second one?
For the second one, when x is equal to 1, the probability is theta by 2 and it is occurring 10 times. So theta power 10 by 2 power 10. For 2,
All
it
right.
is
Yeah.
theta power 20 by 3 power 20.
Huh.
And the last one, 1 minus 5 theta by 6 power 20.
Yeah, correct. So
And then,
you will get your likelihood function.
yeah, and then I took its log and differentiated it to get theta.
Okay, all right. Yeah, that is the correct procedure. Okay. Yeah, okay. So video lectures of tutorial problems, right? So by the end of this month, we should upload by week 8 tutorial problems or videos. So for now, please try to solve the problem on your own. Then you will get the videos also. Yeah, so tutorial problems you can see after the all the activities. So did you never see the tutorial problems? SQT. You never came across the tutorial problems, Kirti? Okay, leave it. So do you want me to solve this problem, or this part is clear? Like how do you find the MME, or using the ML estimator?
If you explain, yeah, it will be helpful, ma'am. Please explain.
All right. So if we first we'll find the method, first we'll find using method of moment. So how will you find, what should be your first step when you are finding the method of moment estimate? What should be your first step? So we first find the expected value of x, right? So if you go back, you see you have x given and fxx given, right? So x is taking the value 1, 2, 3 with probability theta by 2, theta by 3, 6 minus 5 theta by 6. So expected value of x is given by sum over x time fx of x, where x, in this case, x is varying from 1 and it goes to 3. So if you solve it, if you find the expectation, so it's basically 1 times theta by 2 plus 2 times theta by 3 plus 3 times 6 minus 5 theta by 6. So once you do it, you will get 9 minus 4 theta by 3. Okay, so this is your M1. We say this is my M1. Now you have to find the theta here. So, and what is M1? M1 is nothing but x1, like the sample mean, x1 plus x2 plus up to xn by n. And the samples are already given to you. So from there you can find this value, fine. So once you find this value, you can easily find the theta here. So theta is going to be 3 times m1, 3 times m1
9.
minus 9. So this is going to be 9 minus 3 m1 by 4.
Okay.
Okay. And when you have to find using ML estimator, so first write what is the definition of likelihood function. So likelihood function is x1 to, so likelihood function is given by product of your distribution, right? So fx of xi of theta, right? I is varying from 1 to n. Now, if you go back here, so for 1, it is theta by 2. So likelihood function is, for 1, it is theta by 2. For 2, it is theta by 3. And for 3, it is 6 minus 5 theta by 6. But let's see here that 1 is coming out to be 10 times. So we'll have to multiply this 10 times. So it will come out to be theta by 2 to the power 10. theta by 3 is coming for 20 times. So this is going to be theta by 3 to the power 20. And 6 minus 5 theta by 6 to the power 20 because it is occurring 20 times. So this is your likelihood function. So also we can ignore the constant, right? So your likelihood function will be proportional to theta to the power 10. So 10 plus 20, it is going to be 30, theta to the power 30, and 6 minus 5 theta to the power 20. Now, how do you find the theta from there? So we take the log, right? Both sides will take the log. So if you take the log of L, it will come out to be 30 log theta plus 20 log 6 minus 5 theta. Now you want to also differentiate it because you want to maximize your likelihood function. So in order to maximize, we'll differentiate it. So once you differentiate it with respect to theta, you will get 30 upon theta plus 20, 6 minus 5 theta into minus 5, right? And this you will have to equate to 0. So once you do it, you will get your theta. So this is the general procedure that you will follow for any problem where you have to go through ML estimator or MME estimator. Like these are the general procedure. The same thing, take any problem and you go through the same approach. It works.
Okay, okay, thanks.
Okay. Yeah. Okay. Do you have any other doubt? Any doubt from B-Gate? Okay, if you have nothing to ask, then we can close the session. Is it fine? Starts to seem too much difficult. Okay, so yeah, but you'll have to keep practicing and try to learn. So once you get the concepts very right, it won't be so difficult for you. Okay, so if none of you have any doubts, we can close the session. You can drop off now. We need to have more sessions on concepts and interactions. Yeah, that will work. Okay, so we had started our office hour session, right? So how many of you had participated there? So the office hour sessions were supposed to deal with like if you have a problem in understanding the concept, you could have put the concept in the form, and we'll take it from there and explain you the concept. But most of the concepts were coming from like, there were no concepts in the form. It was just solve, like, I couldn't understand this activity, I couldn't understand this problem from practice. So that office hour was not supposed to be like that. It was just like an open session.
Do we have now? I don't think we have now.
We have closed it now because we were getting all those AQ 8 point, like 4.4 something like that from tutorial 1, this problem. So it is not supposed to be like that. So if you want to if you want sessions that are based on like concepts, then that will be better. Like if you can if you then you should also like participate.
Okay.
Yeah, but ma'am, what we can do actually is like maybe every session, first 5 minutes or 10 minutes, have a interactive session wherein people will tell difficulties on this portion like that. Then we can just basically muzzle around and pick up some 4 or 5 concepts. Then mute everybody. Then take through all these things for next maybe about 30 minutes. Then have a break of 5 minutes. Have some interaction. Again mute everybody, and that way only it will work. Because I have seen the session, the way it goes on is basically like some questions will come. Then it will keep on keep on discussing. And what happens is basically, you know, all people sitting around, they might get impassioned, and that is why you can see that the interactions on the whole this thing, even though you see some 90 people, 120 people and all sitting, you see only 4 or 5 people talking. It is because of this actually. Okay.
Yeah, so
what we need to have is very clearly select some, explain it, then have a break, then again close everybody, mute everybody, then take another 20-30 minutes. Like that we need to organize, and towards the end, like maybe if it is a 2-hour session, the last 20 minutes take for problems. And for that problems also, it has to be like you can just continuously solve it. Okay, solve it and ask only people, like people can raise whether they have understood or have not understood. Okay, that is the only thing. So if somebody is telling I have not understood, we can just repeat it. That's it. But we should not basically diverge from that and move into something else, then come back again and all those things. That then becomes a personal discussion kind of this thing where everybody else will be simply watching over.
Yeah, right.
We lose out important.
Yeah. So keep that. We have to organize better, because I have been honestly speaking, most of the sessions I get very impatient. Okay, and the second thing is sometimes it is very difficult to make head and tail out of it. Okay, then what I do is that I go back into the lectures and all and do things on my own.
Okay.
So this has to get organized. Then only people will feel value of it actually. Right.
Yeah, right. Okay. So do you think getting the office hour session back will be a good idea?
Yeah, office hour session has to be back, wherein you block interactions for certain period of time. Like I said,
and open it only for a small time.
Yeah. Then take some concepts, explain it thoroughly. Then, like if somebody is interfering in between, it goes into a havoc actually. Okay.
Yeah.
So 20 minutes after listening, if somebody has not understood, the next 5 minutes he can raise that this thing. Then we can go back and all those things. But it should be on that model only. Otherwise, it will not go on like this. Otherwise, It has to be a continuous open session. Continuous open session means it can go on for hours, like 3 hours, 4 hours. It keeps on going, wherein people can just come on. Those kind of sessions also are there, wherein the teachers will be available. Anybody can raise any question. Others,
Yeah,
if they want to watch.
I think you're talking about CT something.
Yeah, so anybody can ask any question. Others, if they want to watch, they can watch. Otherwise, they can go and have some tea and come back. They can raise this thing. So that goes on like 4 hours, 5 hours, 6 hours, and all those things. That is a different model altogether, actually.
Yeah.
Okay. Yeah. Right.
Okay, so we can bring in back the office hour session. So like I will request all of you to, like, whenever you feel any difficulty in the concept, not in the problem, because if you have problem in the like if you have any doubt in the problems, there is always solution available on this course, right? So I will suggest, please put the concept, like what if there is a concept, what is the part that we couldn't understand. So then it will be much useful, then that session will be very helpful. So I will request all of you, like, please fill the form, and then we'll continue the office hour session. So one session will keep open, one session will keep where we can discuss the concept itself, right? And one is our regular solve with this. That will work. Yeah.
Right.
Okay. Any other feedback? Anyone? Any idea? Okay, so for today, let's close the session and then we'll meet again on Monday.
Thank you. Thank you.
Yeah. Okay. So you can drop off now. We'll meet again on Monday.